Hello and welcome to this lecture. In today's lecture we are going to explore some more about pointers. A little bit more about pointers. We are going to do pointer arithmetic. Then very related to pointers is dynamic memory allocation, how to allocate memory dynamically. So it quite relates to pointers. So we are going to look at dynamic memory allocation, and then we are going to look at inline functions. A part of functions has been remaining since the last lecture, so we are going to complete functions today. So what we have learned so far in pointers is this: the star or the asterisk is the value at address operator. It gives the value at an address, and the AND operator, that is the address of operator, gives the address of a variable or of a value. Now consider the following program segment. You declare an integer int a, and you declare an integer pointer int star p, and p points to a, that is p stores the address of a, right? So now suppose that you want to store the value 5 in a. What are the ways of doing this? You can either say that a is equals to 5. Now this stores 5 in a. Another way of doing this using pointers is that we know that p points to a. P stores the address of a. So we can do like this: value at address of a, that is value of p, and p points to a. So value at p is 5. So this also does the same thing. You are actually saying that value at address of a is 5. So ultimately 5 gets stored in the value at address. So this is correct. Now this is the way you do using pointers, and this is the way you do using normal values. Now in the previous lecture you learnt call by reference. That means you pass address to the functions. Now let us write a program based upon call by reference. Let us write a program that swaps values between two variables. So we have two variables a and b. We swap values. So how you would swap values is, we know how would we swap values. We have done in the first lecture. In one of the first lectures, we took a temporary variable and saved a's value into it, then saved b's value into a. So b is equal to a. Now we have the a's value stored in t, and we want it into b. So b equals to t. So this way we have exchanged the values of a and b. Let us write a function for this, but using pointers. Let's do it. So as usual, we have included standard input output header file. Then we have the main function. Let's write a function called swap. Now swap returns nothing, so we write void swap, and it will accept two pointers, the pointers of the two variables whose values we want to exchange, and those two variables are integers. So how will we collect pointers? Normal variables we do like this: int b. But if we want pointers, so we have a star here. So int star a and int star b, which implies that a is a pointer to an integer and b is also a pointer to an integer. What we are going to do is nothing but taking a temporary variable and saving value of a into temp, and value of b then will be replaced by a and a is by b. So a temp equals to a, right? We have saved the value of a. Now a is free for us. So now let's save b into a. Now we have the value of a, so we can save a's value into b. So b is equals to temp. So this way we have done it. But we did this using values, but we are collecting the values or the collecting the addresses into pointers, right? We are using pointers, so we have to use values. If you say A is equals to B, then it will mean that that means B stores address, A also stores address because it's a pointer. Now you are exchanging address, you are not exchanging values. So you should exchange values. So for values, use a value at address operator. So star B. Now again, let's go through this once again. We have a temporary variable. We store the value of A. So value of A is stored into temp. Now A is free, so inside the value of A we put the value of B, and inside the value of B we put temp. Notice that we have not used star in case of temp. We have not used the value at address operator because temp is a normal variable, it is not a pointer. Star always applies to pointers or addresses, and A and B are pointers, so to access the value the pointer is pointing to, we use the value at address operator. So we have our function ready, but we haven't declared it. So let's declare our function. It returns nothing, so void. The name of our function is swap, and it accepts integer pointers, 2 integer pointers. So int star comma int star. We write this and a semicolon, which signifies that this is a declaration. Now inside main, now we will have to call this swap function. So let's declare some 2 variables, int x and y, right? Actually we want to exchange the values of x and y because x and y are the variables in our main function. So we want to exchange values of x and y, and we pass the addresses of x and y to the swap function. Now it collects those addresses into pointers. Now A and B point to x and y. So let's first initialize x and y. X equals to 5 and y equals to 10. Now let's print their previous values %d, and %d, right? X comma y. So we have printed previous values of x and y. Now we swap these values. Now swap receives addresses because we are receiving these into pointers, so we will have to pass addresses. So we will pass and x and y, the address of operators. Now let's printf the new values. So go to new line and new values %d and %b, and we are printing the same like we did before, but this time the values will be the new ones, right? So let's run this program and check this works, if it works perfectly or not. So this is the output. Previous values of x and y were 5 and 10, and now the latest values are 10 and 5, so these are exchanged. Okay, now let us jump to another concept, pointer arithmetic. Now pointers are numbers, right? Addresses are numbers, and you can apply maths to numbers, right? So you can also apply arithmetic functions or arithmetic operations to pointers also, but there is a little difference. So to summarize it, let me draw some memory space. Let us name this memory space as I, and it contains the value 5, and we assume that its address is 65,000. Now this is a number, right? And this 65,000 is stored into another variable, that is the pointer p. Now what I've drawn can be summarized from this code. I is an integer, p is an integer pointer, and p stores the address of I, hence p points to I, right? Now Observe carefully. What if I do I plus plus? I contains the value 5, and if I do I plus plus, it means that I equals to I plus 1. We are incrementing I by 1, which is nothing but what will happen is 5 plus 1. The value is 5 and we add 1 to it, so it gives 6. But what if I do P plus plus? Again, you can expand this. P is equals to P plus 1, and what it will give, you can also imagine that what it can give is 65,000 plus 1. Now naturally you would say that the result would be 65,001, but this result is wrong. Why wrong? Because you are doing pointer arithmetic, and pointer arithmetic is quite different. The result it will give is 65,004. Now why 65,004 is the bigger question here. Now when you apply the incrementation, or when you apply any arithmetic to a normal variable, it applies it to the value. Now pointer variable does not store a value, it stores an address. Now when I say P plus 1, it means that we want the next integer, means next integer, right? P plus 1, because we are incrementing the address by 1, but actually the pointer is a pointer to an integer. So consider it like this. We have a list of integers and the pointer is pointing to the first integer. When I say increment the pointer, now where will the pointer go? Pointer will point to the next integer. Hence when we apply arithmetic to pointers, it will go to next integer, or whatever the next pointer it will point to. Same if I do plus 2, then it means next of next. That means the second integer, right? The second integer. Now the question remains is why it is incremented by 4. So for your information, let me write this. Any integer in C is either 4 bytes or 2 bytes long. 2 bytes long or 4 bytes long, which means that you have 4 bytes whenever you declare an integer. When you say int I, the compiler reserves 4 bytes for your variable inside the memory. So why 4 bytes or 2 bytes? So there are some variations. 4 bytes if you are using Visual C compiler, and 2 bytes if you are using the Turbo C++ compiler. The space depends upon what type of environment you are using. Turbo C is 16-bit environment, Visual C++ is 32-bit environment, so that's why it depends. Now we are using Visual C++, hence it is incremented by 4. If I say again P++, again it will be incremented by 4. That is, it will point to next integers. Now in a similar way, if you do P minus minus, what you will get is 65,000 minus 1, which is nothing but 64,996. This 1 is actually 1 into 4, right? So we have talked about the size of an integer here. Now what are the various sizes of other data types? What are the sizes of other data types? So for int you have 4 or 2 bytes. We have made it clear why. For character, for a character variable, only 1 byte of memory is reserved. And for a floating point number, for a float, you have 4 bytes. Now how do you determine the size of a variable? If you don't know what environment you are working, do this, right? Printf, there is an operator actually available with C. So the size is actually a number, so %d for a number, and you apply an operator which is known as a size of operator. Let me write that in different color. Size of, there is no space in between, size of. If you want the size of a character, so you write char, and so this way you can obtain the size of a variable. Okay, now to make it more clear, now to make the concept of pointers more clear, let us consider this pointer, int star p. That means p is a pointer to an integer. Now assume that p stores some address of an integer 3000. For simplicity purposes, we take the values 3000. Now what will happen if I do p equals to p plus 5? Now obviously it is not going to be 3005. It is for sure. So what is the size of an integer? Size of an integer is 4 bytes, right? Now how do you calculate what p will point to when we do this operation? So it will point to, it is incremented by 5. So 5 times 4, 4 into 5 is 20. So the next value is actually 3020. When we add 20 to it, it gets 3020. So this is the way you solve pointer arithmetic. Pointer is quite different. Values are quite different. Pointer arithmetic depends upon the size of the data type or size of the value the pointer is pointing to. Okay, now let us jump to a different topic, memory allocation. Now, as the name suggests, memory allocation deals with the allocation of memory space when you declare variables. So when you declare variables, where you declare variables, so you have your function void main or any function, you declare your variables at the top of the function. Whenever the function just starts, at that time you declare your variables. That means you declare your variables before using them. So here you declare variables. Then you take input, then you process values and produce output. So this is the general structure of your program, right? Now what happens in this process? When you declare variables, the compiler does nothing but it actually reserves memory space. Reserve or allocates memory. Allocates memory for your variables to store values. And this memory, whenever you declare variables at the start of any function or at the start of your main function, this memory is allocated at compile time. Allocated at compile time. Now compile time means what the compiler does is it allocates relative memory, because memory is allocated when you run the program. But when the program is compiled, the compiler already sets what relative locations will the variables acquire when this program is run. So this type of memory which is allocated at the start of main when you declare variables is called static memory or compile time allocated memory. That is, the memory is static. Once allocated, it's allocated. It is deallocated, which means it is freed when your program ends. So this is called static memory allocation. And another type of memory allocation which is quite popular is called as dynamic memory allocation. dynamic memory allocation, what it does is it actually allocates memory. It actually allocates memory at runtime. Runtime means while the program is being executed, while it is running, based on some instructions, it reserves some space. It allocates at runtime. So you have your function main and other statements here. You declare your previously variables and other statements, and in between, if you try to allocate memory here, then it is called dynamic. Right. Now you are not allowed to declare variables here. You are only allowed to declare variables here. So how would you allocate memory? Here is there are some functions in the standard C library which allow you to allocate memory dynamically. Now this dynamic memory is actually allocated in a part of memory called heap. Allocated in heap. Heap is a part of memory that is common to all of your functions or all of your programs. So dynamic memory is allocated in the heap. This you should remember. Now let us look at the functions that deal with dynamic memory. So the C library provides us 4 functions for doing operations related to dynamic memory. Let me list all of the 4 functions. One is malloc, second is calloc, malloc, calloc, free, and realloc. So these are the 4 functions available with us to perform functions related to dynamic memory allocation and deallocation. So let us look at each one of them. Malloc actually reserves a block of memory. It reserves one block of memory. What calloc does is it reserves multiple blocks of memory. Malloc and calloc do the same thing. They actually reserve memory, but malloc reserves one block and calloc reserves multiple blocks. Free, as the name suggests, it frees memory allocated by malloc or calloc. It frees memory. And realloc actually reallocates memory. So if you run out of memory allocated using malloc, you can reallocate that memory to a wider space. So this reallocates. Now let us say you want to allocate one integer. Right. Now you have to allocate only one integer, so you can use malloc because it reserves one block of memory. Right. Now you can allocate this using malloc, by calling the function malloc and passing it how much bytes you want to reserve. So we know that integer is 4 bytes. So this way 4 bytes are allocated in the heap. But how will we access those 4 bytes that are allocated in the memory? We need something. We need a pointer to point to that memory so that we can use the value at address operator to obtain that value which is stored, or we can store using that value at operator in the heap. Right. So actually what malloc does, it returns us the pointer to which the memory is allocated. Right. So it returns but it returns, it does not know what. When you say, you just give it how many bytes you have to reserve, right? You just say reserve 4 bytes. So malloc does not know for what purpose are these 4 bytes. It does not know, are these for an integer or a character or a float. So therefore it returns something that is void star. So it returns a void pointer because it does not know, it cannot return an int star or a float star, so it returns a void star. Now you have to convert this void star to some meaningful pointer. That means if you have allocated for an integer, so you convert it to an integer. How you would convert it is using this. Let's say you want to allocate an integer, right? You want to allocate memory for an integer. So you would need an integer pointer to point to that memory. So you write int star p. So you have declared a pointer. Now let us allocate memory, malloc. Now observe carefully that instead of directly using 4, what I am using is size of int. So this makes my program foolproof, right? Whether I am on Turbo C or I am on a 32-bit system like Visual C++, it doesn't matter. My program runs perfectly, right? So size of int. So it gets 4, and 4 bytes are allocated. Now malloc returns a void star, but we want an int star. So what we do is just we typecast. Remember typecasting we did in one lecture. You can also typecast pointers. So void star is typecasted to an integer pointer. How you would do is just write int star here, int star inside brackets. So this is how you allocate memory for one integer, and you can access this using star p. Star p equals to 5. So this 5 gets stored in the value allocated by malloc, in the memory allocated by malloc. Okay, now let us say you want to allocate 3 integers. Right, you want to allocate 3 integers. Now malloc reserves only one block of memory. Now you want to allocate 3 integers. How you would reserve memory for 3 integers? You can make use of calloc because it reserves multiple blocks. So you can reserve memory for multiple integers, right? So for 3 integers we are using calloc. So, and you go about the same way. You have already declared the pointer int star p here, and just use this pointer. P is equals to, now you want to type, you will have to typecast this void pointer which is returned by calloc or malloc into a meaningful pointer, which is int star right now for us, because we are storing integers. So int star, and we allocate memory calloc. Now calloc needs the number, how many blocks you want to allocate. So we pass it the number 3. We want to allocate 3 blocks, and blocks of what size? It also needs blocks of what size. So we can say we want 3 blocks of the size of an integer. So size of an int. So this way you can allocate memory for 3 integers. Now what it does is, actually, let me draw the memory layout, how calloc allocates memory. So it allocates 3 blocks of memories, each of them containing an int. Now when you just say p, p actually points to the first block, right? It returns the address of the first block. Now how will you access the integers of the second and third block? To access the integer of first block, you say star p. So it will give value of 1, right? When you say star p plus 1, so p plus 1 actually points to the second, right? Just now we did pointer arithmetic. When you increment a pointer, it actually points to the next integer or next data type. So we incremented the pointer, p plus 1 points to next int. So gives star p plus 1 gives value of the second, right? Value of the second integer, and this is by p plus 2. P plus 2 points this, star p plus 2, right? Third. Okay, malloc and calloc done. Just remember the syntax of malloc and calloc. Malloc syntax is it needs just the size, how many bytes you have to allocate, malloc. And calloc needs two parameters. One is how many blocks you want to allocate and what is the size of each block, right? And this is what these two functions want. Let us look at the function free. We are just remaining one function, free. Now you have allocated these memories and p points to the first block. How you would, if you want to free this memory, so use the free function. If you have no use of that memory, so you should always free any occupied memory, because memory is like money for computers. When it's free, it's good for the computer. The computer runs fast. So free, we have to pass the pointer. Now don't pass the value. Always pass the address. Pass pointer means you should pass the pointer only. So this actually frees the memory, right? It's just as simple as that. But it frees the memory. It does not delete the pointer. The pointer is as it is. Pointer is as it is. It just deletes the memory. Now this type of pointer which points to nothing is called as a dangling pointer. Right. This is what you have to know in this lecture. Now one last topic is remaining, is that of inline functions. Let us do inline functions now. Now this topic is not related to whatever we have done so far. Inline functions, let us put it this way. We have our main function here, and inside the main function you are calling a function called fun, right? And you have your function fun defined outside, right? You have some statements here. Now how does the control go in any C program? It goes sequentially from top to down. First this statement is done, then this, then it goes to fun. Now whenever it finds a function call, it directly jumps to the function, right? It jumps to the function wherever the function is there in memory. It gets executed and then it returns back to the spot where it jumped from. So what happens is, when it sees the function call, it saves the return address. It saves from where it is going and goes to that function, executes, completes that function, and comes back to the return address. Now this is by default. Normally this happens, and this involves actually jumping of control, right? Now jumping of control takes time, because you have to save a return address, you have to transfer your control to that function, then execute and then return to your calling function, your old function. So this takes time. Now what happens when you declare a function as inline is that whenever the compiler sees a function call, it actually replaces that function call with your function, with your body of the function. It directly replaces your function call with the body of your function. So actually this happens. Your function is replaced by your body of your function. The call is replaced by the body. Okay, quite a clutter here now. Let's clear the screen. Now how do you define an inline function? Inline is a keyword provided by the C language. You just write inline and the function as it is, normal function. So you had void fun and the body, and this statement is inside the function. Now whenever the compiler sees a function call like fun, it will be replaced, it will be deleted, and it will be replaced inline. It actually replaces inline, copies the body of the function and replaces the function call with the body of the function. Now this fun call is replaced by this statement. So inline functions actually avoid jumping of the control when a function is called, but eventually it makes your program larger. Your program occupies more memory space because every time you call a function, the statements get replaced. The statements get copied in place of that call. So eventually your program becomes longer. So with this we come to an end of this lecture. If you have any queries or suggestions, feel free to contact me on this email address. Thanks for listening.